and welcome to this video on forces. We have that a crane suspends a 200-pound steel beam horizontally by support cables, have negligible weight attached from a hook to each end of the beam, and the support cables each make an angle of 60 degrees with the beam. We need to find the tension vector in each support cable and the magnitude of each tension. So to solve this problem, we're going to use polar coordinates. We're going to use some physics, and we're also going to use, I think that's pretty much it. Yeah, and solving equations, linear equations later on. So let's look at what we have here. So this beam is suspended by support cables. We have the support cables right here. And there's a tension vector in each support cable. Because here we have this vector trying to keep the beam from falling, and the same with the vector right here. And those vectors are pointing upwards because the force tries to keep the beam from falling. So it's going opposite to falling. And then, so we're going to call those vectors T1 and T2. And there's a third vector here, third force that is important to take into account in this diagram. And that force is related to weight. This beam is definitely suspended up in the air, but there is the force that is related to weight. So let's write W for weight. That is trying to get this beam down. Now to find that vector W, we're going to go with 0 as the first component because this force is totally vertical, pointing downwards. And we usually write that as 0I or just nothing at all. And then because this vector is pointing downwards, we have a negative component for the second component. And it has to do with that 200-pound weight that we were told about. So it's going to be minus 200. The second coordinate is going to be minus 200. In other words, we have minus 200 times J. So W is actually minus 200 J. For those of you that don't remember what I and J are vectors in the plane. Here, we're looking at the plane. And I and J are these unit vectors that are right here. I is this vector that goes one step to the right and 0 steps up or down. And J is this vector that corresponds to 0, 1. And those are canonical vectors in R2 in the plane. Okay, so there we have this. Now, T1 and T2 are vectors that are also in the plane. So they will be written in terms of I and J. But we don't know a lot about T1 and T2 at this point. So we're going to get some information about T1 and T2 from the graph using polar coordinates. If we imagine that plane XY is right here, so the origin of the plane coincides with this point, then we'll be able to say that T1 has a positive x coordinate and a positive y coordinate because we have that T1 is in the first quadrant of this plane. And using polar coordinates, we can actually say that T1 can be seen as the following. We have the x component that is directly related to the cosine of 60 degrees right here. When we need to take the length of T1 into account, or magnitude of T1 into account, we actually have T1 in magnitude multiplied by the cosine of 60 degrees, and that's the x-coordinate of T1. So here we're using that x can be written as r cosine of theta, where r is the distance between the origin and the location of the point, and theta is the angle between the positive x-axis and the vector. So there's that, and to get the y-coordinate we're going to use y equals r cosine of theta, which in this case is going to be the r, so the distance between the origin of this plane to where the endpoint of T1 is, and that's the magnitude of T1, multiplied by the sine of 60 degrees. Okay. Now we move on to working with T2. And we're going to do something very similar. So this time, our plane is going to have this point right here as the origin. So T2 is in the second quadrant of the new plane. And we can see that the first coordinate of T2 is going to be negative because we're in the second quadrant, and the second coordinate of T2 is going to be positive. Now, because we have 60 degrees right here, and the full thing would be 180, the angle we see here is actually 120 degrees. 120 degrees plus 60 degrees is 180 degrees. So for T2, we will have this representation of T2 in terms of its magnitude. And then instead of the cosine of 60 degrees, we have the cosine of 120 degrees. And then the magnitude of T2 gets multiplied, and that was with I, so we're missing an I here. And then we add the magnitude of T2 times the sine of 120 degrees. Okay, so we have equations that tell us about T1 and T2, and we can actually write those equations a little bit more explicitly. Like here, T1 is actually the same as T1, and the cosine of 60 degrees is a half. So here we have a half of I. And then we have T1 again. And then sine of 60 degrees times j. Sine of 60 degrees is square root of 3 over 2. So we have plus T1 magnitude square root of 3 over 2 times j. And then we check what happens with T2. The cosine of 120 degrees is actually related to the cosine of 60 degrees. This cosine is going to be negative though, so we take the negative of the cosine of 60 degrees. Or we can use a calculator to compute this. We have T2 multiplied by minus 1/2 instead, so minus. And then a half of I. And the sine of 120 degrees actually coincides with the sine of 60 degrees. So we just have square root of 3 over 2, and we missed a j here. There you go, j. Okay. So here we have T1 and T2 written in terms of their magnitudes. And the next thing we want to do is we want to use some physics. the system we have here is in equilibrium, then the total force acting on that we see here in this system should be equal to 0, the 0 vector in R2. And the total force corresponds to the addition of forces. So what we should have is that T1 added with T2 added with W equals the 0 vector, in other words, 0I plus 0J. This equation is very important. This equation will allow us to find everything we need to know about T1 and T2. So this is the equation that comes from physics. Let's write that equation more explicitly using the expressions we have for T1 and T2 and W right here. So we're going to move on to the next page. And we have T1 plus T2 plus W equals the 0 vector. And then T1 was magnitude of T1 times 1/2, and times I was magnitude of T1 times square root of 3/2 times J. And then we have T2, and then magnitude of T2, and there was a negative sign in front of it, and then 1/2 of I. Then we have magnitude of T2, square root of 3/2 times J. And I'm going to move this a little bit to the left. So here we have this. And plus W, and W was minus 200J. And this should equal the 0 vector. So we have 0 in I and 0 in J. So we're saying that T1 times 1/2, we can write that as in magnitude. So magnitude of T1 over 2 times I. And let's rewrite this term as square root of 3/2. Magnitude of T1 times J. And then minus magnitude of T2 over 2I, and plus, just removing those parentheses right there. So we have square root of 3/2 times magnitude of T2, J, and then minus 200J should be equal to 0I plus 0J. And now we're going to collect like terms, or same thing, we're going to add vectors going component-wise. First components get added up. Second components get added up. So we have magnitude of T1 over 2 plus, or better, minus magnitude of T2 over 2. And there's nothing else with I. And then square root of 3/2 times magnitude of T1 plus square root of 3/2 times magnitude of T2, then minus 200. All that goes with J equals 0I plus 0J. And here we have first component of a vector plus second component of a vector, and the whole vector should be equal to the 0 vector. So we should have that the first component of the vector, so here we have what is besides I, should be 0. And at the same time, the square root of 3/2 times T1 plus the square root of 3/2 times the magnitude of T2 minus 200 should be 0. Okay, and one thing we can do with these equations is we can manipulate them. For instance, here we can multiply both sides of the equation by 2 to get rid of that half that we see. And we end up with t1 minus t2 equals 0. And in a very similar way, we can multiply everybody here by 2 over root of 3. The 2 will get rid of the half, and the root of 3 will get rid of this root of 3. So we end up with t1 plus t2 multiplying everybody by 2 over root of 3. So 200 gets multiplied by 2 over root of 3, and they should be 0. So we can, at this point, do various things. One of them is that we can say from this first equation that T1, the magnitude of T1 and the magnitude of T2 are the same. That's something we could see from the diagram, but we just got it algebraically, so that's good to have. And then here, this equation right here is telling us that when we add the magnitudes of T1 and T2, we get, and we're moving this constant over to the right, 2 multiplied by 200, that's 400. We'll keep the root of 3 where it is. So there we have this answer. But because the magnitudes of T1 and T2 are the same, when we add those magnitudes, that's the same as having twice the magnitude of T1 or twice the magnitude of T2. Same thing. Equals 400 over root of 3. And then we divide both sides of the equation by 2, and we end up with magnitude of T1 equals magnitude of T2 equals 400 divided by 2. That gives us 200 divided by 3. This 200 over root of 3 is part of our answer because we want to find the magnitudes of the tensions. Those tensions are have this magnitude 200 over root of 3. And then last thing we can do to find T1 and T2 is we can go back to equations of T1 and T2 in terms of magnitudes. So when we go back to those equations, we get T1 equals magnitude of T1, which is 200 over root of 3, multiplied by 1/2, and then that's the first component of T1. Then magnitude of T1, that's 200 over root of 3 times root of 3 divided by 2, and that's the second component of T1. So this gives us, let's see, 200 times 1, root of 3 times 2, 200 over 2, that's 100 over root of 3i. And then the square roots go away together, and we end up with a 100j. And remember that T2 is very similar to T1, but T2 had a negative first component. Or if you use the equation for T2 in terms of its magnitude, you just get to a negative component. We'll just end up with a very similar vector. So we will have this one still going up. So this is going to be T2. So we have concluded that T1 and T2 are tension vectors given by those equations right here. So this is our T1, this is our T2. And the magnitudes of those tension vectors, which are forces, is 200 over root of 3. Okay, if you have any questions, let me know. Thank you for watching this video. Bye bye.